Hello. This is a live session 2 of the points of topology in PTL part 2 course. So this shall be working numerous Castling antimatrix. So in this session we saw the purpose of this session are to basically problem solving. So please try to make use of this session. Okay. So before starting the session, please let me know, do you have any problem or any doubt from the previous session? Please let me know. Do you have any doubt or any problem from the previous session? Please let me know.
No, no, we got contact.
Okay, thank you, Mustaq, for the confirmation. Okay, let's wait for a few more minutes so that other student also can join. Okay, so let's start the problem. So in previous session, we have done few problems around compactness, right? So today we shall again continue from the compactness thing. So 1 minute, let me open one trace. So yesterday there was a so in the last session we were doing in the last session we are doing some problems and then the session stops. So in this session we shall repeat that too. Okay, so let me write it down, the statement. 1 minute, hold on, please. Oh, so the statement is as follows. Let f of x to y be continuous map. Okay, and let x be compact. Then show that f of x, that is nothing but image of f compact. Okay, please try to prove this by yourself, take your time. F x image of compact, please try to show it by yourself. That means here basically what we need to do, we need to find an open set. I mean, sorry, in order to show compact, what we need to do, we need to show that any open cover has a finite subcode. That means we need to start with some open cover and finally come up with some finite subcode, right? Please try to figure it by yourself at the first place. Then I shall explain. Mustaq, please try and let me know the argument. So the hint is as follows. So hint is that let U alpha collection of the U alpha B and open cover of fx. Now from this what you need to now need to construct an open cover of x, then then it will follow automatically. So please try to do that, take your time. Oh, okay, so the solution is as follows. Mr. are able to figure out? So are able to figure out? Okay, so let me explain. So basically the thing is, since U alpha is an open cover, so that means what? The collection F inverse U alpha is an open cover of x. Why? Because since fx equal to union of U alpha, this implies what? This implies x belongs to union of f inverse of U alpha, correct? X equal to union U alpha, right? So this implies what? This f inverse U alpha is an open cover for x. Now since x is given to be what? X is given to be finite. So that means what? This this open cover f inverse U alpha has finite subcover, correct? So that finite subcover means what? So call it f inverse u alpha I is equal to 1 to n. Okay, so that means what? That means x equal to f inverse of union of u alpha I. So that means what? Fx equal to union of u alpha I is equal to 1 to n, and that implies what? This collection u alpha I is an open cover of fx, correct? So this is the argument. Is the argument clear? Please let me know. Basically here what we are doing, we are not really not doing anything complicated. We basically start with an open cover of fx, and from that open cover fx we came up with an from that open cover we come up with some subcover of f of x, and then the rest of the thing follows automatically given because x is given to a compact, right? So that is the thing. So that's the argument. Okay. Okay. So please let me know, is the argument clear to you or not, or else we shall move to the next problem. Okay. So the next problem. So the next obvious problem is, what about the converse? So please try to figure this out, that how the converse will hold, or does the converse hold actually or not. Please do think and figure out. Please take your time. That means what? You need to come up with a counter example, okay, which is domain is compact but codomain is not compact. Okay, so this is the thing you need to figure out. Please take your time, let me know. Note that what we need to do, we need to come with example having uh, so that domain is compact, codomain is not compact. Okay, So, okay, so please try to think what that are possible. Okay. What are the possible solutions? Please try to think and figure out. So, see, so we can have a map F, okay, from 0, 1 to, okay, so what example we need to construct? We need to construct an example where code, where domain is not compact but codomain is compact, correct? Have a F x to some singleton x. The map is R going to singleton x. So clearly codomain of this function is compact, of course, but domain is not compact, okay? So this is the argument. Codomain is compact but domain is not compact. So yeah, so this is one of the following examples. Okay, I hope this is clear. Now the next thing. The next question is as follows. The next question is, what is that? Let x be a cofinite space. Show that x is compact. Basically, this theorem tells what any cofinite topological space is always compact. Okay, so this is a thing I want need to prove or show or prove or disprove, whatever it is. Okay, so please try to do it by yourself. Okay, so basically cofinite topological space means what? Any, that is any set which is open if and only if its complement is finite. Cofinite is complement is finite. Okay, so please try to figure this out or try to figure out a proof. Please take your time. I shall be back in a few minutes. So, okay, so Mustak, are you able to figure out this problem? That is cofinite response to compact. Do you have any idea or any guess? Okay, so let me explain. So basically, the thing is, see, since x is cofinite, that is u subset of x open if and only if x minus u is finite. Okay, so let u alpha be an open cover for x. Okay, so choose alpha belongs to this. So that implies x minus u alpha not finite. Okay. Now after this, can you please uh, think that how to come up with the finite subcover? The only thing is that x minus u alpha, this particular thing contains, and I mean this is a finite set, right? So all infinite element contains inside u. The only finite elements of x belongs to outside u alpha. So how to capture those elements with some open cover? Please do think and figure out. Please do think. Uh, So the trick is as follows here. The trick is as follows. So let me write it down. Okay. See, since x minus u are not finite, so let's denote the elements by x1, x2, x3, dot dot dot. Okay. Now, so this xi belongs to u alpha I for some I. Correct. So this implies what? This implies x equal to union of u alpha I equal to 0 to n. So this implies what? This implies the collection opens at u alpha I forms a finite subcover of X. Okay, so this is the argument. That's all. There is nothing much to explain. So the trick is that we have to first choose a fixed open set, and that complement contains a finite set. So call it x1, x2, xn, and then x equal to union of u alpha. That's all. So the collection u alpha forms a finite subcode of x. That's all. So there is nothing much to explain. Okay, so that's all. So I hope this argument is clear. So next question is that show that x with co-countable topology never be compact. Previous quoted co-finite topology, then he open set complement is finite. Here the question is co-countable topology. You need to show that X is contained to be co-countable topology, it can never be compact. Okay. So that means what? You need to come up with an open cover which does not have been a finite subcover. So yeah, so this is the trick. So please try to think and please let me know the arguments. Okay, take your time. Okay, Mustaq, so do you have any idea or any trick in your mind which can solve this problem? Mustaq, do you have an idea on a trick in your mind which will solve this problem? Okay, so the idea is as follows. I mean, there is no idea, it's a trick actually. So since X is an uncountable set, so consider a countable collection x1, x2, x3 dot dot dot. Okay, choose u1 to be x minus x1, x2, x3 dot dot dot. u2 to be x minus x2, x3 dot dot dot. Similarly un minus 1. Okay, so it's clear that this collection ui I equal to 1 to infinity, it's an open cover for x, correct? However, but this collection does not admit finite subcover. Why? Because why? Because if this collection ui is finite, so call it n, then sum of xi does not belongs to this union, which is a contradiction because x must contain x, right? So the thing is, if this collection have a finite subcover, so take the union and take the large index of the union. Okay, so sum of the x lies outside of x1, x2, xn, correct? And this shouldn't happen, right? So this is the argument. So that is why this collection does not cannot have a finite subcover. Consequently, this open cover, any open cover does not have a finite subcover. Okay, that is the argument. Next question is, it's a simply computational question. Show that set of matrices in MNR with a determinant 1 is not compact. Set of matrices is of MNR in MNR with a determinant 1 is not compact. Okay. So yeah, so basically here you have to use the fact that the hint is use Heine-Borel theorem. Okay, so please think out, take your time, let me know. That means compact if you are closed bounded, you have to check whether it's closed or you have to check whether it is not bounded. So either one of that hold does not hold. That is the argument. So please do think, take your time. Okay, so Mustaq, are you able to figure out how it can be solved? Any case or any idea? Please let me know. So yeah, so the trick is as follows. Okay. So first of all, the point is we shall claim is the collection the set X. Okay, claim X is not compact since it is not bounded. Okay, it is not compact since it is not bounded. Okay, so see, so consider the matrix A is equal to 0, I mean, diagonal 1 1 1 n 1 by n and rest 1 and rest everything is 0. Okay, so determinant of A is of course 1. However, norm of A is equal to root over n square plus 1 by n square. This is going to infinity as n is going to infinity. So that means what? This collection X is not finite. Okay, so yeah, so this is the thing. So yeah, so that's why, sorry, what? basically, sorry, it's not finite, basically it's not bounded. Okay, so this is the argument. Okay, so yeah, so this is a tree, that is determinant A is equal to 1 given that x is not bounded. So that means what? That means what? X not compact. Okay, so then now the next question is mm, next question is next question is like a circle is compact in R2. Circle is a compact subset of R2. Please try to prove that. For this, for you, what you need to construct an open set. Sorry, you need to basically circle. I mean, okay. Okay, circle is compact. Basically, you need to use the fact that it's closed and bounded. Okay. So yeah, so please do think and let me take your time. You need to show what is closed and bounded. Okay. Here the same hint. Heine-Borel theorem. Okay. Please do think. Take your time. Let me know. Hi, unfortunately, due to some technical issues, uh, there is some internet problem. So
You
yeah,
are not audible.
uh, I'm audible now.
Yes, now audible.
Oh, but due to some internet issue, there is some miscommunication here. Anyway, so I shall start now. Where's that? 1 minute. Just hold a moment, please. Mustak, is the screen audible? Sorry, is the screen visible properly? Mustak, is the screen visible? Can you please confirm? Mustaq, is the screen visible? Can you please confirm?
Hello?
Is the screen visible? Can you please confirm?
Yes.
Okay, thank you, Mustaq, for confirmation. Okay, so hmm. So basically, the last problem which we are dealing is that the following what that circle is component art. We need to show that. That means what you need to do. We need to show that circle is closed plus bounded. What is a circle? Circle is nothing but all those points in xy such x square plus y square equal to 1. So it's a close. So the closeness can be seen by using sequential criteria. So it's closed. Why? Basically, you have to use sequential criteria. Okay. So so that means what you need to choose a sequence x and y. I'm going to explain and assume that the sequence x and y and this point belongs to the circle. You have to show that the point of convergence also belongs to circle. Okay. So please do think and take your time. Let me know. Please do think, take your time. Let me know. Mustafa, I will figure out by using sequential criteria how to show that this circle is closed. It shouldn't be difficult anyway. Okay. So okay, so the solution is as follows. See, first of all, we have this xn. 1 minute, what is this thing now? There is some sync issue. Huh. Okay. So let xn, yn be a sequence circle converge into x and y and going to xy. Okay, now we need to show that the point x belongs to y1. Now since x and y and going to xy, that means what the point sequence x and going to x and y and going to y, correct? That means that xn square plus yn square going to x square plus y square. However, this thing exactly equal to 1. That means what? By uniqueness, we limit x square plus y square equal to 1 by uniqueness, right? This implies what the point xy belongs to the circle. Is it clear? So that means what? That means circle is closed. And of course, circle is bounded. That means what? Circle is compact. Okay, is it clear? So yeah, so this is argument. So please go through the argument once again and let me know. So in this argument, basically we have shown the circle is compact. So for showing compact, what we need to do, we need to show that it is closed and bounded, right? Bounded is obvious. Only we need to show closeness, correct? Now closeness can be seen from the fact from the sequential criteria. That means what? We need to choose a sequence x and y in a circle and assume that sequence converted to point x. We need to show that the point xy belongs to a circle. Okay, so that's what the sequential criteria means. Okay, so this is the argument. Okay, so I hope this argument is clear. Now next problem. Next problem is that show that ellipse is compact. Show that the ellipse is compact. Okay, ellipse means what? Ellipse means x squared by a square plus y squared plus b squared equal to 1. Show that it's compact. How to do that? So basically, you have to use the same sequential criteria thing for doing that. However, there is another way. Basically, you need to construct the another trick is that construct a map from circle to ellipse. Okay, Please try to figure out the map by yourself. Take your time, let me know. So, Sak, are you able to figure out what the map between circle and the ellipse will be? Okay. So let me read the map for you. So from circle to ellipse, points will be x comma y going to x comma y. So this map, if this map is a homeomorphism, correct, and circle compact. So this implies ellipse is also compact. Okay. So basically, this xy going to x comma by, this is a map by stretching the corners, correct? So yeah, so that's the compact thing, right? So that's, so there is nothing much to explain. Okay, so now the, so next question is, show that the hyperbola, this is what hyperbola, is not compact. Of course, the point is by looking at this diagram, this is a hyperbola generally. Of course, this is not compact, period is not bounded. However, you need to explicitly show it's not bounded. That means for any n you can get a point inside the hyperbola whose norm is greater than or equal to n, right? So that's what you need to show. Yeah. So please do think, figure out, and let me know. Take your time. So, Mustaq, any idea or any argument or how to show it's not compact? See, the point is you can choose the point root over x equal root over n plus 1, y is root over n. Okay, so of course x square minus y square. However, x square plus y square, this is what? This is 2n plus which going to infinity as n sufficiently large, right? So this implies what? This implies x square minus, this implies hyperbola is not compact, correct? So this is the argument. So is the argument clear? Basically, we construct a point root over x root over n plus 1 root over n, which is the point in the hyperbola, which has norm going to infinity as is going to infinity, right? So that's why hyperbola is not a compact set, right? Is it clear? Okay. So the next problem is that uh, suppose if x to y be continuous, the next problem, 1 minute. Okay, so the problem is that a continuous y Hausdorff, okay, then y is Hausdorff plus compact. Then f is continuous if and only if the graph of f, that is x comma fx, x belongs to x, is closed in x1y. If x2, so y Hausdorff compact, then f is continuous if one graph is closed in x1y. So okay, so please try to do it by yourself. There is nothing, the hint is, basically the hint is that use the previous theorems. Okay. So please do think, take your time, let me know. So the thing is, so see, so define a h from x cross y to x comma y going to fx comma y. Okay. Now since y Hausdorff, so its diagonal is closed. That implies H inverse of diagonal of y closed in x cross y, correct? That implies now, so H inverse of diagonal of y contains what? It contains all those point x, y such that f of x equal to y, correct? And this is my graph of f, right? So this implies what? Graph of f is closed in x cross y, correct? So this is one direction. In this one direction, we have showed that if f is continuous, y is compact, Hausdorff, the graph is closed. Please try to do the reverse yourself. Reverse, please try it by yourself, or else I shall get back to you. Please take your time. So for the converse, the argument is as follows. Mustaq, are you able to figure out the any argument of this? Mustaq, are you able to figure out any of this argument? Please let me know. Okay, it seems not. So okay. So basically, he, so we have to assume the graph is closed. So assume graph if it's closed. Okay, we can assume that, right? Now here is a picture, and suppose this is graph of f. Okay, we have some x, we have some y. Okay, now graph of f is closed. What do we need to show? We need to show f is, and we need to show f continuous. That we need to show inverse image of closed set is closed, correct? So if subset of y be closed, okay, so this is some f. Okay, now consider pi to inverse f. So this will be this line only, correct? Intersection graph of f, so it will give this line only, and take pi 1 of this, there will be this one. Okay, so this is nothing but f inverse f, correct? Right, so that implies what? If is closed, pi 2 is continuous, so this is closed, graph A closed by definition, so the intersection is closed, and pi 1 is closed, so this implies f inverse f is also closed. So this implies what? F is continuous. Okay, so this is the argument. I hope this argument is clear to everybody. Okay, so I have this argument is clear. Please, Mustaq, please let me know whether this argument is clear to you or not, or else we shall get back to another problem. Please let me know, Mr. Mustaq. If yes, please let me know. Then I shall state our next problem. So basically, this problem has two parts. One part is that if it's close to the graph, if it's a continuous graph, it is closed. So, and the second option, second is that graph if is closed, we need to show that f is compact. Okay, f is continuous. So, Mustaq, please go through the argument once again and let me know do you have any question or doubt, or else we shall move to the next problem. Okay. Okay, Mustaq, is the full argument clear? Please let me know. I hope so it's clear, so there is nothing much to explain. Okay, so the next problem is that, suppose if x to y be continuous, or x is compact, or x is compact, and y is Hausdorff, then show that f is closed. That we need to show that x carries a closed set to a closed set. That's what I need to show. Okay, so there is nothing much to explain. So please do think carefully, let me know, and try to solve it. Use the previous theorems. So see, so let let f solution is let f be closed in X. We need to show that f of f is closed, right? Now f is closed. This implies what? F is compact because closed subset of a compact space is compact, correct? That implies f of a is compact because continuous image of compact is compact. That implies f of f is closed because compact subspace of a Hausdorff space is closed. Okay, I hope the argument is clear. There is nothing much to explain. Okay, so f is closed. So the argument. So basically, this argument is nothing but what? So if it's continuous, X compact, Y Hausdorff. So if it's a closed one, that's all. So closed as a compact is a compact, compact as Hausdorff is closed. So these are the things I have used for this problem. There is nothing really much I have used. Okay. So Mustaq, please let me know whether everything is clear or not. Okay. So yeah, I hope that's clear. So there is nothing much to explain. So okay, anyway, if you have any doubt, please let me know. The next problem is that let A and B be compact subspaces of Hausdorff space X. Show that A and B can be separated by means of open sets. A and B compacts of Hausdorff space X so that A and B can be separated by means of open sets. That means what? You need to show that what is that? Basically, you need to show that they are open set U and they are open set V, okay, which contains A and contains P, and their intersection is norm. This is what you need to show, okay. Now, so please try to figure this out. You have to use the compactness as well as the Hausdorffness very cleverly. Please take your time. Let me know. Okay. So the thing is that So basically the thing is that we have the for each A belongs to, for each B belongs to, we shall get open set UA and open set VB such that UA intersection VB empty, correct? Now what we need to do is that we need to set U to be union of UA and V to be intersection of VB. It turns out to be empty, and now this forms an open cover of A, and similarly VB forms an open cover of B. Okay, so those are the things we have to use in order to conclude that this is an open set. I mean, this their intersection is empty, and this U and V are the open set containing A and V containing B. Okay, so these are arguments. So basically, you have to use the compactness, allowance, the Hausdorffness. There is much to explain. Okay, so yeah, that's all. So please do think about it in your spare time, and please let me know whether you are able to manage it or not. If not, then please ask the question in the next session. I shall get back to you in the next session. Okay, so for the timing, that's all for this session. Okay, okay, so it's over now, so we shall end here. Let's meet in the next Sunday. Thank you.